Good evening, everyone. Welcome, and special congratulations for turning out in spite of all the weather warnings. I'm Tony Symes. I organise monthly lectures for the Herschel Society, and tonight's lecture is New Results from Gaia, Crystallising White Dwarfs, Spinning Minor Planets, and Our Galaxy's Dark Matter Halo. And our speaker tonight is Professor Michael Perryman. The Herschel Society holds its lectures here with the support of the Bath Royal Literary and Scientific Institution, and the Society brings together like-minded people who are interested both in modern astronomy and the historical contribution of the extraordinary Herschel family. So I've put flyers out on the seats, which you might be interested in. This lecture is being recorded. For those of you in the room, if a fire alarm were to sound, the normal instructions are to proceed out the way you came in, down those stairs and out through the door. We don't turn right as we did before, because that area where we used to assemble is fenced off now for building works. So we cross the road carefully and assemble by the obelisk. And if the flames prevent you from going down those stairs, you go to the door at the back through the Lonsdale or dinosaur room, down the stairs and out through number 18. But of course that won't happen. And we also have a Zoom audience, and for those of you on Zoom, please keep your video and microphone off during the lecture, and please put any questions that occur to you into the chat channel for answering afterwards. Now, looking ahead, our next event will be Tuesday, the 11th of February, and we've got, the title of the lecture is John Dilwyn Llywelyn, the Welsh John Herschel, ? And it's by Stuart Helmsley Rice. But back to tonight, and we're very lucky to have Professor Michael Perryman, who lives in Bath. During a 30-year career with the European Space Agency, he was the scientific leader of the Hipparcos and Gaia space astrometry missions. He's won various awards for his leadership of space astrometry, including the very prestigious International Shaw Prize in Astronomy in 2022. Let me hand over to Michael Perryman.
Thank you, Tony, and thank you all for coming. The last time I was here at astronomy, the previous, I think, Herschel conference was Professor Chris Lintott from Oxford University and the celebrity presenter on Sky at Night. And Chris gave, I thought, a wonderful talk on chance in astronomy, I think it was called, or discoveries, chance discoveries in astronomy. One noticeable thing sitting in the audience, he gave many examples of this chance discovery, but almost all of them were from the US. They were either US ground-based telescopes or US scientists or NASA missions. And of course, NASA specializes in these wonderful pictorial Hubble Space Telescope, James Webb Space Telescope, Cassini, Voyager. These are spectacular missions for the public, I think, to appreciate some of the majesty. My talk will contrast with Chris's in three ways. First of all, he had a much bigger audience. Second, I'm not going to be talking about chance. Chance plays a big role in astronomical discoveries because there's so much we don't know about the universe, and it makes it's so important, I think, in almost every sphere of research. But I'll also be talking about a specific European project, and that is called Gaia. And I think some of you will know that. Those of you who are more interested in amateur astronomy will know that. But I'm going to talk about Gaia. Now, Gaia is a purely European space mission. Its goal is to measure the positions of stars Now, if that sounds really bizarre, in measuring the positions of stars, are we serious? The point is that if we measure these positions extremely accurately, and we continue to make these measurements over a period of several years, we can start seeing tiny motions in the stars and the sky. And these motions unveil this rich sort of panoply of insights into what our galaxy is, how our galaxy originated, and much more. So I'm going to be talking about Gaia. Gaia has been extremely productive in terms of scientific publications. There's something like 8,000 or more scientific papers that have come out of Gaia. So I'm not going to touch on all of those 8,000. What I've decided to do is to pick out three examples out of perhaps several hundred, 200 or 300 that I could have chosen, 200 or 300 that areas where Gaia is really making a tremendous advance. But for each of these, I think I need to give you a little bit of background, a little bit of explanation, for you to be able to appreciate what is it we're trying to understand and what is it that Gaia is contributing. So I'm going to focus on three areas. Before I get into that, I will give you a quick picture of what Gaia is, where it sits in the history of this field of research, and why it is so transformational. So, help. Where's our technical man?
Can you use the arrow on the laptop? Here it is.
The advancer is not working.
Try now.
Thank you. You better stand there and hold my hand for one. So in the introduction to this talk, Tony put this quotation up on the left there. It's by Ethan Siegel, an American who writes frequently on astronomical topics that you can find on the web. And Ethan said, one of the most remarkable space science missions that most people have never heard of is Gaia, a mission by the European Space Agency to map out the three-dimensional positions and motions of more stars in the galaxy than ever before. And another quotation that I picked out to introduce you to the topic is one of the scientific publications that put this in the introduction, was that galactic astrophysics, so the study of our galaxy today, is currently in a similar phase as geography was in the 15th century. Large parts of the Earth were unknown, only crude maps of most of the known parts of the Earth existed, and in a similar analogous way, Gaia is making this huge advance in our understanding of the structure, the evolution, the history, the composition of our galaxy. In the entire history of this field, which really started with the ancient Greek astronomer Hipparchus, about 200 or 300 years BC, so more than 2,500 years ago, more than 2,000 years ago, I'm just going to pick out two events. I don't have time to go through the sort of long and detailed history, but there's two perhaps transformational events that will help set the scene. One was in 1718, so 300 years ago, Edmund Halley had been comparing the maps of the heavens that existed at that time with the maps that Hipparchus, the ancient Greek, had made 3,000 years before. And he found that three stars, here is Aldebaran in the area of the Orion. And this is just a little schematic. If you look there, you can see that the star had moved between the map that Hipparchus had created 2,000 years previously and his own observation. And he found this for two other stars, Sirius and Arcturus. And at this point, the first realization that the stars are not static in space, that they're actually moving through space. Now, if you go, let me just make an aside, if you go out into and see the night sky, of course it's changing night after night, but the majority of that is due to the fact that the Earth is rotating. The stars themselves are remaining fixed, or essentially fixed. They're not absolutely fixed, which is where Gaia comes in. The next event that I want to pick out is the fact that we can measure the distance to the stars. Now, I'm going to just explain this question of parallax, and I think a number of you will know the phenomenon, but I'm going to go just through a little exercise so we're all, as people say, on the same page. When Copernicus came up with the idea that the Earth was moving around the sun rather than the sun moving around the Earth, there was an immediate consequence of that, which is that if the Earth is going around the sun, then a nearby star should appear to move with respect to the background star due to the effect of parallax. Now, let's all indulge me. Let's all just do this little experiment. Hold your finger up. Hold one finger up. Choose something in the room. Close one eye. And then open that eye and close the other eye. And your finger appears to move with respect to the background. Yes? Everyone got that? Yeah. Right. And we're going to do exactly the same with the Hipparcos Space Astrometry mission and the Gaia Space Astrometry mission. In one sense, it's trivial. It's trivial trigonometry to first order. The practical difficulty in doing this is that these angles are so immensely tiny. So this was the idea. Copernican theory, Earth moves around the sun. You should be able to distinguish the motion of a nearby star compared to the background star. And it took 250 years between people setting out on this journey to try and measure parallax until around the late 1830s, when three astronomers almost simultaneously trying to measure this effect of parallax. So this 250 years was marked by a continuous improvement in astronomical instrumentation, gradation of the circles that are used to measure these small angles. And eventually in 1838, the distance to the first star was measured. Now, I think the great problem with astronomy is that the scales are so enormous that it's very, very difficult to convey the enormity of space. But the nearest star is about 3 light years from us. Proxima Centauri is about 3 light years. It would take light 3 years to travel from Proxima Centauri to us. Now, we cannot imagine that. We have no meaningful way of visualizing that. And I like to use another one, which is that if we spaced out every person on Earth, all 7 billion people, and we spaced out each person by 5,000 kilometers to the next person, those 7 billion people would reach the nearest star. So you can imagine perhaps that this angle that you need to measure is very small. Now, what's the big picture of our galaxy? We're right in the middle of the galaxy, and when you look up into the night sky and you see the Milky Way, this is the plane of the galaxy that you're looking into. This prominent Milky Way band is the flattened disk of our own galaxy. And if we could look outside our own galaxy, it would look something like this. This is the M31 Andromeda nebula or galaxy, and our own galaxy would look something like that. Our sun sits out in one of these spiral arms. It's just one of perhaps 100 billion or 200 billion stars in our own galaxy. The solar system, our own solar system, is of course on a tiny, tiny scale on this. And the distance to the center of our galaxy, about 30,000 light years, 10,000 parsecs. The first satellite launched in 1989, Hipparcos, that I worked on for 17 years, and we thought was making a dramatic improvement in distance measurements, measured out to the kind of distance that you can see with that yellow circle. It was a very significant advance, but insignificant on the scale of the galaxy. What Gaia has done is to extend our direct distance measurements out to this kind of scale. Gaia was launched in 2013. It's still operating today. It will be switched off on the 15th of January next year after about 10.5 years in orbit. And I'm going to show you some of the results that we're getting from this. Now, finally, to set the scene, I'm going to give you a little bit of a historical, a quick journey through the history of this field. How accurately have people been able to measure these tiny angles that are necessary to measure the distances to the stars and how the stars are moving through space? And on the horizontal axis there, you can see time, extending from the present day back to about the time of Hipparchus the Greek. And on this axis, I'm giving a scale that we refer to as arc seconds, seconds of arc. Now, there's 360 degrees in a circle. Each of those degrees can be divided into 60 minutes of arc, or arc minutes. Each of those arc minutes can be divided into 60 seconds of arc. And then we can divide those seconds of arc into a thousandth, a millisecond of arc, and a millionth, a microsecond of arc. And that's a logarithmic scale, so a factor of 10 on each of those coordinates. On the right here, just to try and give you a little bit of a sense of what these angles mean, Hipparchus, the ancient Greek, back in, back here was measuring angles with the accuracy of about the size of the full moon. The human eye, I've done it again, all right. The human eye, resolution is about 30 seconds of arc. So the early catalogues of Tycho Brahe, Flamsteed, and so on had an accuracy of about 30 arc seconds. More recently, up until sort of the second half of the last century, ground-based telescopes could get down to something like 1 second of arc. And this is where the atmosphere hits you. We're living within the Earth's atmosphere, and light coming through the atmosphere is distorted by the troposphere in particular, and this puts a limit on the accuracy to which you can measure star positions from the ground. So this is what created the need to go to space, that you can get above the Earth's atmosphere, and what we can see now is that this sort of straight line improvement of accuracy over time, it's on a logarithmic scale, but it's a log linear evolution in time. Hipparchus made a very sudden transformation in that, jumping down to about 1,000th of an arc second, and Gaia has gone a factor of 1,000 more than that in the last few years on top of Hipparchus. In terms of numbers of stars, Hipparchus measured about 120,000. We thought that was incredible at the time. Gaia is measuring 2 billion. Now, for those of you who find it difficult to visualize 2 billion, I'm going to show you one of the volumes of the Hipparchus catalogue. And when you open it, you realize why it's not quite as visually attractive as missions to Cassini. I could click through a few pages that will all look the same. And on each of those pages, there are 100 stars. And there are 5 volumes of these, which are, again, for those that remember telephone directories, looks a little bit like a telephone directory. And those 5 volumes contain 120,000 stars of Hipparchus. Now, the question to the audience is, if I printed the same catalogue for 2 billion stars, how many volumes would I need? Does anyone want to give an estimate? I'll tell you what, how much shelf space? Anyone? You need about 10 kilometers of shelf space, printed at the same scale as Hipparchus, to accommodate just the list of stars that we're measuring. So that tries to give you, and that's about maybe 1% of the stars in the galaxy. So it's a very significant fraction of the stars in the galaxy, but there's lots and lots of stars in the galaxy. As time has gone on, what I try and indicate there is the sorts of science that's developed from that. As the accuracies got down to about 1 second of arc or so, then you start seeing the motions of the stars with these latest ground-based catalogues in around the year 1980 or so. The big emphasis was understanding stellar evolution. With Hipparchus came the much better understanding of what's going on in our solar neighborhood, and what we've got with Gaia probing so far out in the galaxy that we're starting to see enormous details of galaxy structure and evolution, which is going to be the subject of the rest of my talk. And this is just a few examples of some of the telescopes throughout history, And this is Gaia. This is the experiment, the payload, the telescope that is being put together on the ground. And what we have is two mirrors, 1.5 meters by 0.5 meter. There's one here, one will be mounted here. And this is all sitting on a rigid silicon carbide torus, which preserves great integrity of positional displacements and so on. You see everyone dressed up in protection suits to avoid any kind of contamination. So that's Gaia. I'm not going to explain how it works. That's the subject of another talk, but this is it, a very, very high technology piece. I think probably many of you saw the images of the James Webb Space Telescope, solar panels being deployed. Gaia had one almost as large, 10 meters, and this is shielding the very, very delicate instruments that are sitting here in this thermally protected shield from the sun. The sun will be illuminating from the back here, and the solar array, this big solar array sun shield, is providing both the power for the satellite but also shielding it from the thermal effects and radiation effects of the sun. Now, that's all I'm going to say. I'm not going to say any more about how Gaia has made these measurements. I think all that you really need to understand is that if we could make these measurements over a long period of time, as the Earth and the satellite go in its orbit around the sun, then you can perhaps see that there is a chance of measuring these distances through the effect of trigonometric parallax and also how the stars are actually moving through space. All these motions are very tiny, almost imperceptible, but they can be measured at this kind of degree of accuracy. And the kind of accuracy, I'll give you one more analogy, which is the 1 microarc second or 10 microarc second accuracy of Gaia is the equivalent of measuring the angular radius of a hydrogen atom viewed from a distance of 10 meters. So again, that's very, very tiny. This shows, over the last 20 years, this is something that ESA, the European Space Agency, created, which is the number of scientific publications per year coming out of the various missions. And you can see there that some of the most productive missions in the past, XMM Newton, it's an X-ray satellite, Rosetta, Cometary Visitor, Herschel, Far Infrared, Planck Cosmic Microwave Background Experiment. And here are the publications coming out of Gaia. So a very large number of scientific publications, of which I'll present a selection today. So I've said the Gaia catalogue contains about 2 billion objects. It's got distances, it's got motions, it's got colors, it's got spectroscopy, and so on and so on. The best positional catalogue before Hipparcos was launched was something called the FK5, which contained 5,000 stars. The Hipparcos catalogue contained 120,000. And as I've shown you just there, the Gaia catalogue contains 2 billion, and I just worked out that if you spent 1 second looking at each of these stars, it would take you 30 years, day and night. So we have gone beyond the time where people look at these individually. These are all now done, analysis, interpretation, and so on, through the computer analysis of very large data sets. So there are many hundreds of new scientific results, and I'm going to break them down into 3 categories. One is the minor bodies of the solar system, so asteroids. Gaia is actually observing many asteroids. The structure and evolution of stars, and the structure and evolution of our galaxy. And what I'm going to do is to give an example of, just one example of each of these, so to go into a little more depth and to explain to you what Gaia is doing. So topic number 1, spinning minor planets. I think this is a great challenge. You know, if you're not involved in these fields, I think trying to get a picture of what it is we're talking about and why it's interesting for scientists to do this, and how is it being done. I think these are going to be very difficult concepts to grasp, but I hope I can give you a sort of big picture and a feeling of the excitement and interest and the discoveries that are being made. So our own solar system, now remember what we mean by that. That's the sun and the planets and the moons of the planets and the asteroids and the comets. Basically, this is before you get anywhere near the next nearest star. This is what's going round our own solar system. And we now know that the solar system consists of the sun, 8 planets, and then countless billions of smaller rocks and solid rocks, icy particles, the asteroids and comets. And what we want to know is more about how the solar system came into existence, how it was formed, and trace back really how our own planets formed, how the moon formed, and so on and so on. And I would say in the last 20 or 30 years, there's been tremendous advances in this. And the solar system ends up being now, I think, a bewilderingly complex and magnificent system where all kinds of strange things are going on. Resonances of moons moving around, moons that have been captured as they've passed close to one of the giant planets, the rings of Saturn, but very complex motions of these asteroids. And I think the point I want to stress here without going into details is that we have, through the ground-based observations, but also satellite missions exploring the outer bodies of the solar system, and especially, I think, with the advent of the discovery of extrasolar planets, that people have worked more and more on models, chemistry models, dynamical models of how the solar system formed. And we have a very good picture now of how the solar system formed. And in just a couple of sentences, I mean, we go back something like 5 billion years, and in this area of the galaxy, there would have been a sort of sea of gas and what astronomers call dust. So this is particles of small compounds or elements that came from previous generations of stars. So, you know, the universe started off mainly as a mixture of hydrogen and helium. As time has gone on, as this material has been processed through stars, it's thrown out into higher elements all the way up: lithium, carbon, beryllium, boron, oxygen, neon, and so on and so on. All the chemical elements that we see now were processed and generated by stars in the interior of stars. And we have a very good picture of that. And the solar system would have been created from these small particles of dust or compounds that existed in this proto-solar nebula. And as they went round and round the sun, particles started joining together, becoming glued to each other if they interacted, and these built up into progressively bigger and bigger particles, eventually forming these sort of intermediate boulders, bigger rocks, and eventually hundreds of kilometer-size objects, which again impacted, joined, coalesced, and eventually ended up forming the planets. So that's the formation of the solar system in a very, very few words and simple words. But the details are well established now. And what we see, if we look down on the solar system, here's the sun. This is Jupiter, the orbit of Jupiter. I guess that's Saturn. And then in here somewhere is Mars. You'll see that in a moment, and the Earth. And we're looking down on the solar system. This is the main asteroid belt, so where most of the asteroids are congregated. These are left over. They weren't gathered together in the early stages of the solar system formation. These are the Trojan asteroids of Jupiter, the Jupiter Trojans at 60 degrees and 60 degrees before and afterwards. And we have a very good understanding of the dynamics, how they formed, why they formed, and so on. Now, what Gaia is doing, at the moment, it's measured or released the information for just over 150,000 asteroids. At the end of the mission, there will be something like 300,000 or 400,000 of these asteroids. And because we're repeatedly measuring the positions of these objects, we can determine the orbits of them. So in this little animation, I can set that running, and we can see the orbits of these asteroids, picking out, first of all, there's Jupiter and the Jupiter Trojans. These are taken away, the main belt asteroids taken away. These are the near-Earth asteroids, and then plunging in just to part of this now into the main asteroid belt, and just for fun, a sort of a simulation. This is now the real orbits of these stars, speeded up, of course, but real orbits measured by Gaia, and the colors there are a representation of the actual colors that we measure with Gaia as well. So they're a little bit accentuated, but remember that all the solar system bodies are not radiating their own light. They are just simply reflecting light from the sun, but they reflect light according to the chemical composition of their interiors or their surfaces. And so these asteroids have very, very different chemical compositions and very, very different colors. So we can tell an awful lot about the composition where they formed from their colors. I'll mention one sort of very strange phenomenon which has been uncovered in the last 10 years or so, and that is called the Nice model, formulated by astronomers from Nice. And if we look along the horizontal axis, this is time, so extending from 0 to about 80 million years. And on the vertical axis, this is the orbit. So you can see here, this is the current orbits of Jupiter. This is the orbit in astronomical units. So this is Jupiter.
Excuse me.
Yes.
When you're standing over there, the Zoom audience can't hear you.
That's not right. I'll try and avoid doing that. So we see these are the current orbits of Jupiter going out to Saturn, Uranus, and Neptune. What is believed to have happened in the early solar system is that they formed in a slightly different order going out from the Sun: Jupiter, Saturn, Neptune, and then Uranus. And the current understanding is that at some point these Neptune and Uranus, in fact all the planets, were migrating very slowly towards the Sun, in some cases away from the Sun, but in these cases towards the Sun. Sorry, away from the Sun. And at one point they hit a kind of resonance and they actually swapped positions. Now, an alert member of the audience will say, how on earth can you tell that they swap positions? Well, the evidence, which is not totally firm at this moment in time, but it's looking that way, you can see that not only from the composition, because the composition of the major planets varies as a function of radius from the Sun, but also as these planets slowly migrated through the solar system after formation, they kicked aside some of these asteroids and forced these asteroids, some of the asteroids in their path, into different orbits. So what you can see, if you're armed with very large numbers of these orbits, you can trace back and see whether you can explain the orbits of these asteroids consistent with the motion of these planets. Now, I'm talking about asteroids, and I haven't yet got to the main point that I wanted to pick out for asteroids, which is the effect of the sun's radiation on these objects. Now, a lot of you will probably recognize this. It's called the Crookes radiometer, and it was a piece of physics introduced by William Crookes in the early 1800s. And did you see that when the light was switched on, the veins within this sort of almost vacuum bulb started rotating? The explanation is actually a little bit more complex than radiation pressure, but for the purposes of this discussion, let's just say radiation pressure. We've got photons we've got light coming from the bulb, and that hits the veins. They're silvered on one side, dark on the other, and this has a differential pressure effect which sends the veins moving. Now, an individual light photon carries a tiny, tiny, tiny amount of momentum, tiny amount of energy, tiny amount of momentum, but it's enough to set this thing in motion. And the same thing happens when you look on the scale of the solar system. And here's the surprising thing that I want to focus on for the next couple of minutes. The sun's radiation pressure has a noticeable effect on the asteroid orbits, which we're seeing with Gaia. The effects are, I would say, in some cases, totally non-intuitive. So you can imagine that here's the sun on the right, If you have very, very tiny particles near to the sun, you might expect those particles to be pushed outwards as a result of the radiation pressure. There's something called the Poynting-Robertson effect, which is encountered in early university physics. And the Poynting-Robertson effect ends up moving these tiny particles into the sun. Now, how does that occur? It occurs because you've got the sun's rays. Take a little particle here, which is going around the sun. You've got the sun's rays coming out and hitting the particle, but the particle, because it's heading round in its orbit around the sun, is actually presenting a tiny part of its projected face to the side, to 90 degrees from the sun. And that is enough to sort of create a braking force on that tiny particle, and the particle ends up moving towards the sun. If the particle is less than a millimeter or so in size, they actually move towards the sun. If they're bigger, something different happens, and it depends on whether the asteroid is rotating in the same sense of rotation as its orbital motion, or in the counter sense of its rotation. So we call that prograde if an object is spinning in the same sense as its orbit, prograde, retrograde if it's spinning sort of backwards, and they can end up spinning in all kinds of ways. And just very briefly, what was realized in about the early 1900s is something called the Yarkovsky effect. And that is that the solar radiation hitting this spinning asteroid warms the asteroid is always rotating, and that energy is re-radiated in the infrared at a slightly later time. All right, it's a little bit like heating of a greenhouse. The sun's rays are coming in, warming the Earth, and the Earth re-radiates in the infrared, which is then blocked by your greenhouse. So, all you need to understand for the purposes of this is that if the asteroid is rotating in one way, the solar radiation is re-emitted as the orbit is rotating, as the object is rotating, and that acts as a tiny force acting on this massive asteroid. And depending on whether it's prograde or retrograde, it can either push the object outwards or move it inwards. Now, you may say, if you've got a 10-kilometer asteroid and the sun's light shining on it, surely that can do nothing. And you'd be almost right, except that over something like 10 million, 50 million years, that is a cumulative effect that just carries on acting. And so for these spinning asteroids, depending on how they're spinning, their orbits and so on, they can be moved into slightly different orbits. And we can start seeing that effect, objects depending on their spin, and we can determine their spin from the light curves. And we can see the effects on the orbits. Now, the reason that's interesting, it was first observed radar tracking back in the 1990s. This particular object was moved something like 15 kilometers from where it was predicted to be. But the reason this is important is that the asteroids that get shifted by this Yarkovsky effect are the smaller asteroids. So asteroids starting off in the main asteroid belt can then be nudged either outwards if they're prograde and inwards if they're retrograde. And these are forming what are believed to be now the majority of the Earth impact asteroids. So every couple of days now, you'll see an announcement that NASA has discovered an asteroid that's heading straight for us or very close to us. You know, we've got doomsday every day now. And these potentially hazardous objects or near-Earth asteroids, many of them are simply coming from this main asteroid belt, perturbed by the Yarkovsky effect. So this is something which, it's an effect which delivers very small, less than 10 or 20 kilometers inside, main belt asteroids into Earth-crossing orbits. And some of them, sooner or later, will perhaps hit the Earth. I'm going to jump this slide. And in fact, I think I'll jump. This is just showing some near-Earth objects that have been tracked by ground-based observers. This is the Earth's orbit in blue, and these are near-Earth orbit objects that are being tracked, and you can see that they are sort of propelled when they get close to the sun into strange orbits. So we are sitting in this kind of shooting gallery of asteroids that are affected by not only the historical remnants of the solar system formation, but also effects which are still ongoing today. Now, still on the subject of asteroids, let me mention this, because if you're an amateur, I don't know if there are any amateur observers in the room, but this is something that really may interest you. If you're not aware of it, then let me explain briefly. There are these words in astronomy: eclipses, occultations, and transits. And they're all sort of roughly the same, one object moving in front of another object. If they're sort of comparable inside, you call them eclipses, like the solar eclipse. If you've got a small body moving in front of a larger body, like the transit of Venus or transit of Mercury moving across the face of the sun, you call it a transit. And if it's a big body occulting a tiny body, so a solar system object occulting a star, you tend to call it an occultation. But they're sort of the same thing, one object passing in front of another. There are planet-planet occultations. First recorded Jupiter occulted by Mars in 1170, described by one of the Cistercian monks and also Chinese astronomers in the East. There were 2 in the 19th century, none in the 20th century, 5 in the 20th century, 5 in the 21st century. The Galilean moons can be occulted. The Galilean moons are occulting a star, another star. And then we've got star-asteroid occultations, where all these asteroids moving around us in the solar system might pass in front of another star, right? You can imagine they might pass in front of another star. So what we now have from Gaia is 150,000 of these asteroids with very accurate orbits, and we have 1.5 billion stars with very accurate positions. So put those two together and you can predict when one of these lumps of rock is going to pass in front of one of the stars. Now, this was all a very sort of hit and miss affair before Gaia, and people would go out, look for an occultation, it was predicted, and then observers would find that this occultation, they weren't at the right place on Earth, or they were setting up the telescope at the wrong time, or whatever, because the predictions were so uncertain. But with Gaia now, the predictions are accurate typically to a few seconds or a couple of minutes, and you know where it's going to pass on Earth. So this is the path of an occultation event. I think this was Io passing across the face of the Earth at some particular time. This is the line of centrality, and any observer around that line can point their telescope up in the sky, get the signal from Gaia, and observe this transit. And there's many amateur sites where you can find these predicted events, and people can then pool their observations. So a particular interesting one, again, enabled by Gaia's accurate orbits of Neptune's moon Triton and all these stars, is that on the 5th of October 2017, amateur astronomers were alerted to this potential occultation event. And you can see there was something like 100 different observers who observed this. And what you can see there is, in each of these cases, a slightly different profile. This is the background star, the starlight, and then as the Triton passes across the face of the star, it occults the light. But what you can see, something strange, is that right in the middle of these events is a little positive burst of light. And if you're right on the line, of centrality, these increases in light are very dramatic. And what this is the atmosphere of Triton. So the atmosphere is actually acting like a lens. And as Triton moves across the face of a star, as you get precisely at the point of centrality, then the starlight from the background star is being lensed by the atmosphere around Triton and gives this peak. And there's lots of interesting things coming out of that. Well, there are many other things going on in the solar system and many examples of different investigations that are being explored with Gaia. I don't have time, I think, to say more on that. Crystallizing white dwarfs. I'm not doing very well in terms of time, am I? We'll do this one quite quickly. What we see with Gaia now, we can actually do a real travel through the local solar neighborhood. You've all seen this on Star Trek. Star Trek is just animations. This is the real McCoy. This is the real distribution of stars. Amongst these are lots of white dwarfs. I should say that really stars are very diverse. We've got something like 100 billion in the galaxy, and I think to comprehend a little bit the problems that astronomers faces, I think it's fair to say that everyone is different. It's like all 7 billion people on Earth are different in some sense. Every star is different in some sense. Either its mass, its radius, its chemical composition, its rotation, its magnetic field, turbulence, whether it's in a binary system, and so on and so on and so on. So they're all very, very different. And what one is trying to do is to understand the sort of different evolutionary pathways, and the distance of these stars is a very essential ingredient in mapping out the evolutionary pathways. Something like, so here's a little AI image of different people, different population. So we have a very good understanding of how stars form from interstellar gas and dust. We've got a very good understanding of how they evolve over hundreds of millions of years. How some of them explode as supernova, depending on their masses, and the vast majority of stars end their lives as white dwarfs. They burn on this is the main, so-called main sequence, if you know anything about astronomy. This is the Hertzsprung-Russell diagram. You plot the luminosity of a star, how bright the star is, against its color or its temperature, and stars line up with these sort of very prominent features. This is the main sequence where hydrogen is burning in the core of the star. This is where the bigger stars get towards the end of their life and become giants. And down here, 97% of stars end their lives as white dwarfs, and they explode and flip over onto this white dwarf sequence. What I'm going to be talking about there is this little feature, this tiny little feature here. And the point to appreciate is that this is again the map of the luminosity obtained with Gaia for stars within about 300 light years. And these features are very well understood, but there was a strange one here, which was considered to be particularly curious. And what happens then in these white dwarfs, this is the nearby star Sirius, and this is its companion, the white dwarf companion, Sirius B, which was discovered, I think, in 1917 or thereabouts. So white dwarfs are these very exotic objects. When the star comes to the end of its life, the nuclear hydrogen burning ceases, the star collapses, and it forms a very compact object that is no longer undergoing nuclear fusion. And that object then just sits there and cools and radiates for the rest of time, for the hundreds, the billions, tens of billions, or hundreds of billions of years into the future. Well, that's sort of a little animation showing one of these stars exploding, but anyway. In terms of how old the universe, I have this little aside here. We think the universe is about 13.7 billion years, our galaxy just a little bit younger. The solar system, everything that we know about the solar system points to an age of about 4.5 billion years. It's an interesting topic to look at how the age estimates of the Earth have evolved over time. Many of you will know that there was this biblical chronology that put the age of the Earth at about 6,000 years, so 4000 BC, by Bishop Ussher, Bishop of Armagh. But this wasn't just one sort of eccentric theologian working on his own. People like Kepler and Newton also believed that this was the age of the Earth at that time. The Comte de Buffon, a Frenchman who was very famous for his collection, I think in 28 volumes of all knowledge of nature, did his own experiment and came up with 10 spheres, iron spheres of different sizes, and he calculated how long they took to cool and extrapolated to form the age of the Earth, which he estimated to be about 75,000 years. And the current age is something like 4.5 billion years. So what happens as the white dwarf then starts cooling is that something similar to what happens when water converts from ice to a liquid to a gas. If you provide a constant amount of heat to water in its frozen form, the temperature will go up until the ice starts melting, and then it sits there for a period of time at constant temperature while the ice is melting. And this is called a phase transition. While this phase transition is going on, and the same happens then, you start heating it, the liquid, and then when the liquid reaches boiling point, it starts turning to a gas, but sits there at the same time. And what's going on with the white dwarfs is the same in reverse. The white dwarf is cooling. The white dwarf starts off as a plasma, a gas, you can think of it as a gas, and then at a certain point, this gas, this plasma, starts crystallizing. And models of that crystallization are able to reproduce exactly this feature here in the white dwarfs, and the plot of the white dwarfs magnitude versus color. Now, what this means in turn, it was considered to be a little bit of a surprise. It wasn't particularly well understood initially, but someone pointed out that there was some theoretical work done by 3 people independently in the 1960s, 2 Russians and 1 American, Edwin Saltpeter, and they predicted that these white dwarfs should be seen to cool. And Pierre-Emmanuel Tremblay from the University of Warwick put this explanation out in 2019 and came up with a model to explain that this little feature here is the white dwarf actually crystallizing. And what will happen in our own sun, so you can think of this as this will happen to our own sun, and we can predict roughly when this will happen. Our sun will continue, it's been burning for about 5 billion years. It will continue more or less in the same form for the next 5 billion years. And at that point, it will cease its nuclear burning, turn into a white dwarf. And in about another 5 billion years, the sun will start crystallizing from the inside out at a rate of about 1 or 2 centimeters a year, according to these theoretical models. Right, my final topic, and I've got 10 minutes to do it, so I'll comfortably manage that. And I'm going to switch now. My topic 1 was on asteroids, looking at what we were understanding about the solar system, the formation of the solar system, and so on. My second topic was on a subset of stars in the neighborhood of the sun, these white dwarfs. And my third topic is what we call stellar streams, which is very critical in understanding the formation of our galaxy. Now, let's go back to that image that I showed of M31. This is what our galaxy would, M31 is roughly what our own galaxy would look like. Today, we have a picture of our galaxies, our neighboring galaxies, and the universe as a whole, is that our galaxy, this flat disk with spiral arms, is sitting in a big cloud of dark matter. All right, so we're sitting in this halo of dark matter. And if you know a little bit, or you've heard about these models of cosmology, you know, the current idea, the current paradigm in cosmology is that something like, I always forget these numbers, is it 5% of the matter is normal matter, 23% of the gravitational mass in our neighborhood, in the universe is dark matter, and something of order 73% is what is called dark energy. Don't ask me anything about these, I'm not your right man to ask. I do star positions, not cosmology. But the point is, this turns out to be an extremely successful model that allows us to replicate a lot of the structure that we see in the universe, in the galaxies, and so on. And in this model, when people run these big computer simulations, what we see is that a galaxy like our own, over the billions of years of that galaxy's existence, it will capture other galaxies, tiny galaxies that happen to wander too close to our own. And what we're starting to see in our own galaxy, and this is an artist's impression of our galaxy, but built up with these vestigial remains of cannibalised galaxies that have been captured by our own. Now, that's a lot to get your head round. Our central galaxy disk is quite a heavy concentration of stars all rotating around the centre, and we're believed to be sitting in this huge extended halo of dark matter. According to these theories and these models, which started emerging in the late 1990s, we should, if we had accurate enough measurements of the motions of stars and the distance of stars, we should start to see these, what are called halo streams, these remnants of these cannibalized galaxies. The interesting thing here, and the reason this is feasible at all, is that as you go farther and further out in a gravitational system, the time scales become longer and longer. The Earth goes round the sun in 1 year. Jupiter goes round the sun, it's further out, and it goes round in about 11 years. Uranus, much further out, goes round in 84, thank you. Neptune, Charles? About 160, I think. And as you go further and further, these timescales get longer and longer. And as you go to gravitational matter, which is falling in the halo of our galaxy, these timescales are tens of, or billions of years. So when you look out, if you could measure the positions accurately enough, you would expect to see these remnants. And I'll show you now a couple of things, a couple of little animations. The first one is, just imagine this is the center of, this dot is the center of our galaxy, and I've taken everything else out. And now I set this little animation of a galaxy being captured by the gravitational field of our own galaxy. And as time goes on, over several billions of years, this galaxy, this cannibalized galaxy, gets stretched out and torn apart as it goes around our galaxy. Now you might think, what hope is there of actually being able to recognize that kind of structure? And the answer is you can, because all of these stars are moving in a very similar way. They will have similar orbits, and if they've come from the same cannibalized galaxy, you might expect them to have the same chemical composition, the same spectral features. And this is indeed what is seen. So this is an animation of the breakup in a little bit more detail of a particular satellite stream called Cetus. And this is our galaxy. This is the Cetus galaxy being captured. And after 1 billion years, the stars would be spread out like that. After 2 billion years, like this. After 3 billion years, it's starting to have gone round 2 or 3 times in its orbit. And after 5 billion years, it's stretched out like this. And according to these simulations then, if you could get the positions and distances and velocities accurately enough, you might see this kind of structure. And this connects with what I think has been a really dramatic advance in astronomical understanding, which is these big numerical simulations of structure in our galaxy. So the first of these, first really big one was run in about 2000, only 25 years ago, and bigger simulations of the whole formation of structure in our universe. So this is a galaxy which is a little bit like our own galaxy, which is extracted from these simulations. And what you find is the structure in these simulations with these sort of puffy clouds and nearby objects. And in some of these simulations, you see another galaxy coming close to ours, and the simulations stop here. And this is very much like the Large Magellanic Cloud. and our own galaxy. So these numerical simulations, when you put in the ingredients of the current cosmological models, which are called cold dark matter, you end up being able to recognize these structures, which we can then see in the Gaia data. Now, the end result of this is that we can now start to see that our galaxy halo is really the graveyard of many other galaxies that have been captured by our Milky Way over the last 12 billion years. And there's a couple of really big events, one called the Gaia Enceladus is the biggest, the Sagittarius is the second biggest. And most of these have now been found. There's more than 100 of these streams that have been found surrounding our galaxy by Gaia. And they provide very strong support for this cold dark matter paradigm. So things are really, I would say, the bottom line message here, however curious this may seem, we do seem to have a very, very good model of how structure in the universe first originated and how it has propagated over the billions of years since the universe appears to have come into existence, replicating the kind of galaxies and structures and neighbors that we see today. And this is all put together in this little animation by one of the discoverers of one of these streams, Malhan. And there's our galaxy, sort of the spiral galaxy in the middle there. And as we zoom out in this animation, you see the individual stars which have been discovered in this Gaia survey, which fit into this model of these cannibalised galaxies. Now, that actually brings me to the end of my presentation. If I had time, I was going to talk about, just raise two separate points, and I will just raise them, and then I will close the discussion. But the first one is, people who know me will probably be sick of hearing this, but is the Earth flat? And I bring this up because growing numbers of people, according to censuses that are conducted both in the UK and in the US, indicate that more and more people are no longer convinced that the Earth is round. More and more people seem to think that there's no evidence of the Earth being round, and they're personally convinced that the Earth is probably flat. Now, this may seem very comical to you, and if it does, I would urge you to read one of my essays on my website where I go into a lot more detail. But I'm not going to put that view graph up, but the same surveys, now these are YouGov surveys, which are considered to be serious surveys. It's how, Nadim Zahawi made his millions from setting up YouGov. And they ask the questions, not only is the Earth flat, but they ask other questions like, is climate change exaggerated? Are vaccinations damaging? Did the moon landing occur? And so on. And it seems that more and more people are concerned are questioning these things. And as far as I have been able to understand, it seems to be that as science becomes bigger and bigger and more complex, fewer and fewer people are actually able to understand what's going on, and more people then want to question the processes that lead to that. They're skeptical of what governments are doing. So it doesn't really matter how many people think the Earth is flat or round, but it does matter if those same people think MMR vaccines are bad, or climate change is not real, or whatever. So I like to just throw that in, because when I'm standing up talking about these very, very big challenges in science, I think a lot of scientists desperately want to be able to bring the rest of the population along with them, explain why it's interesting, explain why it's exciting, explain why it's possible. And we have one eye on the fact that it's all very well explaining it to people who are interested and motivated, but that's not how society is necessarily structured. The other thing I wanted to raise, but just very, very quickly, and I would have gone on if I'd had a little bit longer, is that both of these missions cost ESA around $400 or $500 million. The point I wanted to stress in this is that $500 million doesn't go up in smoke when the rocket is launched. That $500 million goes into European industries predominantly, And those industries are building up the technologies that they need to remain competitive in a sort of ever-increasing, technologically advancing civilization. So economists are studying this. I think it's a very, very interesting topic to try and trace where the money goes. But I'd like you to sort of bear in mind that this kind of exercise is fascinating for scientists, it's fascinating culturally, but it's also very important economically. And I will leave it at that point. So thank you very much for your attention.
Well, thank you very much. I'll hand over the microphone over to Charles to take round. If you've got any questions, please could you just raise your hand and wait for the microphone so the Zoom audience can hear the question.
Hi, thanks for a very interesting talk. Two questions. One is, can you tell me where Gaia is placed, where it's orbiting? And secondly, can you tell me, the sense I get from what you've been talking about is everything is moving at different rates. Does Gaia look at the position of objects relative to others, or does it have an absolute frame of reference?
All right, thank you for both these questions. The first one is, something like the International Space Station is in a low Earth orbit, 400 kilometers or so above the Earth. A lot of, say, communication satellites are put out on the geostationary or geosynchronous orbit around 36,000 kilometers above the Earth. There's a particularly favorable location for astronomical satellites, which is the L2 Lagrange point, the Earth-Moon Lagrange point, which is a position of stable equilibrium about 1.5 million kilometers from the Earth. And Gaia is there, Planck was there, WMAP was there. It's getting quite busy out there, although it's a huge place. So that's the first thing. It's out at L2, so it's a very, very thermally stable environment, gravitationally stable environment, and you get all-sky visibility as the system moves around. The second question is yes, it's very perceptive. The question was, right, you're measuring. So essentially what Hipparchos did and what Gaia does is you're measuring every star with respect to every other star. And you're building up this huge jigsaw of relative positions of this with respect to this, and then as this moves, it's slightly changed, and you measure this, and you measure this, and you measure this, and you end up with this big jigsaw, and you're absolutely right. What is the fundamental? You end up with something which has got actually 6 degrees of freedom, 3 rotational degrees and 3 time-dependent rotational degrees. And the trick is to try and figure out what is your absolute origin. And that is not a particularly trivial thing to do. So to first order, you can connect all the stars to the quasars. So quasars, we assume, are inertial, they're fixed in space. That's not the whole story. There are other things going on there, but to first order, that's what you do. It's not a totally trivial problem, how you fix the origin. And if you don't get the origin correct, then you get an offset in the parallaxes or the offset in the proper motions and things like that. So it's turned out to be a very tricky challenge. It's a little bit like, how do you define the origin of longitude on Earth? Latitude is defined by the Earth's rotational axis. Longitude is an arbitrary choice, chosen by convention with respect to some location in the sky. Thank you.
So you mentioned that the crystallization of white dwarfs happens due to the star cooling down. How do you detect that? Because you mentioned we have actual evidence of that now.
I sort of went a little bit fast through this, and you can't detect it directly. What you can do is to look at how these white dwarfs are piled up in this space of luminosity versus temperature. And what you see is these outliers, these objects that don't sit in exactly the location you would expect them to on the basis of stellar evolutionary models and so on. What you see is that little blip. And when you throw in the models which invoke this cooling going on the inside, which had been predicted theoretically, then that model fits together with the observations. So I think you can be very safe in concluding that this crystallization is going on. We've got good theoretical models which tell us what's going on and can predict the delay in the cooling. It's basically a delay in the cooling. The fact that the white dwarfs are crystallizing introduces a delay of something like 1 billion years in the expected cooling rate that you would expect otherwise. But I didn't explain that very well, but thank you for that.
Could I cheat and follow up on that one? Is it that all the white dwarfs are doing that? Only some of, or only some of
Well, a lot of them will not have yet reached the point where they're cooling. So a lot of white dwarfs are it'll be another, depending on the mass of the white dwarf, it can be maybe another 10 billion years before they start to crystallize. So it's just the ones that happen to be in the right location in terms of their mass and temperature at the present time.
On the same topic, somebody has to ask this: what do they crystallize into?
Into a lattice, into a solid.
Do we model that lattice? Do we know what that lattice is? I mean, it's a big mix
is
of
the
it's a mix
tessellation?
of elements, isn't it? But
I'm going to pass on that. I mean, it's I suppose the same way that.
but it
I mean,
becomes
it's basically heat. You're looking at these. I don't know what the crystalline structure is.
No, but it
may well be in these papers. I haven't looked at that.
But it must be more ordered. I mean, the crystal is
yeah.
much more ordered than the jumble of before, so it must have a order. It's
Well,
interesting question.
it is referred to as crystalline.
Yeah.
Now, to what extent it has a homogeneous crystalline structure, or whether it's simply some kind of disordered solid, I don't know. I've not looked into those papers. I think you'd need to sort of go back to these papers by Edwin Saltpeter in the 60s and look at. I haven't done that.
Well, there's a lot of carbon there, so I'll call it a diamond. Okay?
All right.
I don't have any questions on the chat channel as such, but I got one comment which is interesting. Unfortunately, Gaia did not find Planet 9. And that leads, I mean, that's put in as a comment, but what I'm saying is if there was another large undiscovered planet out there, would Gaia have seen it?
Well, the way Planet 9 is being inferred is through the orbital motion of some of these asteroids. So I think there are direct searches going on now. Is there an object there? It's going to be very, very faint. It's going to be well below the detectability of Gaia. But the way the planet is inferred to exist is through the dynamical motions of the asteroids in that particular area. So they're perturbed by the orbit of this hypothetical Planet 9, and you see these orbital structures in the asteroid orbits. So there's all kinds of things going on in these asteroid orbits that I've not touched on. Planet 9 is a really interesting case. I don't think Gaia is going to make any contribution to that.
Right. It might possibly discover some interesting asteroid motions. Yeah.
Oh, yes. Yeah.
You mentioned at the end there about applications, primarily you seem to touch on communication as an area. And I was just wondering, what do you think the solution to that communication gap is? How do you get more people to, come on that journey with you? It's a hard one. million-dollar problem.
Well, I mean, one anecdote or it's not an anecdote. Is an anecdote something you make up? I don't know. One story that I'll tell you is that when Hipparchos came to an end, when the Hipparchos project came to an end, I tried to write a popular book explaining what Hipparchos was. I eventually got it published by a rather not the best publisher that I was hoping for, let us say. But I got very, very good reactions on what it was and how it was written and the information that it contained. But it turned out that if you publish a book in English, then typically, I was told, something like 40% of the sales go in the UK, if you're a UK author, but 60% will go into the US. So they put my book over to their US collaborators and asked whether there'd be any interest in publishing this book. And the answer was no, because no one in the US had heard of Hipparchos. Now, my goal in writing the book on Hipparchos was because no one had heard of Hipparchos, it would actually be a good exercise to try and inform people about where this money had gone and what it had done, but I could not find a publisher. The same US publisher said to me, we're not going to publish this on Hipparchos because no one has heard of it, but if you'd like to write a book on the Hubble Space Telescope, we'll publish that. To which my reply was, first of all, I don't know anything about the Hubble Space Telescope. And secondly, there are already 50 books written on the Hubble Space Telescope. But they wanted another book on the Hubble Space Telescope, not on Hipparchos. So I can say I tried. But I mean, your question is a very serious one, and I don't know. There are panels on the Royal Society looking at education and outreach and so on. And I think it's a very, very, it's a very, very difficult question. But I think the reality is that you're faced with an increasingly vociferous public who has access to all kinds of, social media. And this is clearly having a very damaging effect in a number of areas. So, I would say, thank you for your question. I don't have any great ideas. The great communicators in science are the people that I think give us the best prospects of reaching out and communicating. But scientists have to try and make that effort, but it's not easy. Bridging the gap between, what I know and what nobody knows. If they don't know anything, they're not going to be interested.
Another question. Roger.
Follow-ons, is it more of the same, just more accuracy in the measurements, or a different direction?
In terms of future missions, I don't think I'm going to see anything in my lifetime. Partly because the technology is going to be very challenging. I think something like the European Space Agency will only take on a new project, if it breaks significantly new ground. Now, from the science that I think we can do with Gaia, I would say that you'd need to make the next step in accuracy something like a factor of 10 or even more than a factor of 10. You could go into the infrared. That would allow you to observe in the center of the galaxy. That would be very valuable. But I would say you need something like a factor of 10 improvement in accuracy. And with that factor of 10 improvement in accuracy, there are lots and lots of very interesting things you could do. One very simple thing would be to predict the orbits of asteroids something like 100 years out in the future, so that you would have 100 years warning of which ones were going to collide with the Earth. I made that point back in 2000. There was a panel under Lord David Sainsbury. They took my inputs, and then 2 years later, the whole panel was scrapped as guidance on future directions for science. So something like Earth impact comes and goes, and I know that Rusty Schweiker, I think he was Apollo 8 astronaut that leads one of these panels on Earth asteroid impacts, has said the only thing that's going to change policymakers' decisions is the next impact. And at that point, people will wake up. But there's lots of things that you could do. I think you'll need something like a factor of 10 or 20 improvement in accuracy, and then you need a much bigger mirror or free-flying satellites. And I don't see the appetite yet for that. I don't see the technological excitement or the direction. I don't think I'll see that in the next 20 years. But it would be good, more of the same, but much higher accuracy.
What range of frequencies does Gaia observe in?
Oh, sorry, I didn't. It's optical. It's a 1 meter array of CCDs, just under a meter by a meter. It's the largest CCD array ever flown in space, manufactured by E2V in the UK, which has actually just been taken over by an American company, Teledyne, so unfortunately. But that's a CCD, so like in your normal phone camera or whatever, so it operates over the sensitivity range of the silicon in the CCD, so about 400 nanometers to just beyond 1 micron. So it's the optical range.
Any more? Can I have one in that case? Can you compare what Gaia has done to what it was predicted it would do when it was funded in the first place?
Yes, I think we can, and I'm writing these sort of weekly essays. If anyone is interested, I should just put that www.michaelperryman.co.uk, and I put an essay out each week, and I often make reference to the scientific case that we made at the time of Gaia's selection in the year 2000, and I would say a lot of what we're doing, a lot of the ideas, a lot of the discoveries that are being made were foreseen, all right? So things like, one of the things motivating Gaia is, can we say more about the structure of spiral arms in our galaxy? Can we say more about the gravitational interaction between the Large Magellanic Cloud? Can we say more about particular phases of stellar evolution, binary stars, things like this? So a lot of it was things that we wanted to know. Now, of course, there's many things that have come out of it that we weren't expecting, but the general directions are what we thought we wanted to do. Now, one of the curious things that has been sort of troubling me a little bit recently is, has Gaia made any discoveries that are absolutely, completely revolutionary, unexpected? And I think the answer is probably no. But I don't know what counts as an unexpected discovery. Maybe crystallization of white dwarfs was one, but it was predicted in. Pardon? Yeah. So there's a lot of incremental advances. I think something like the structure of the stellar streams is one. Growing evidence for dark matter, from some of the dynamical motions. But yes, this is why I contrasted it with Chris Lintot's talk on accidental discoveries in astronomy, whereas Gaia was very much a sort of, we need to know this, and this is what we need in order to be able to understand it.
Well, it looks like we've come to an end. I've got one comment from Dipali. She wanted me to repeat that these results match estimates made by Indian astronomers several thousand years ago.
Well,
I think.
To see her source.
Right. Okay. That was my reaction as well.
Indian astronomers predicted what? Sorry, I think I missed the.
Well.
They predicted the halo streams, or?
Well, this is what I tried to find out. I tried to find out what she was getting at, and.
Maybe I won't
Yes,
go further on that.
I'm not too sure.
Okay. Oh, well, it's good to know. Good to know that we didn't do it all in vain, I suppose.
But
no, I mean, if she has if there are some predictions that were made that she could pass on to you, I'd be very interested. Very interested to see.
I will. If there is anything, I'll pass it on. Would you like to step up to the lectern too?
Thank you, Michael.
While Bob is. I'd just like to interrupt and say that Bob Fosbury here is going to give us a talk on the light and life. Which month is it? April?
March, I think.
March,
yeah,
right.
Yeah. Okay, I just wanted to make a few remarks at the end, and not so much about the science, but I've known Michael for many years, and since the late 70s or even mid-70s, I don't know. And we've never worked in the same place. Michael worked in the Netherlands, in ESTEC, the European Space Agency. I also worked for 26 years for the European Space Agency, but I was in Munich, Germany, and I was working on the sexy telescopes like Hubble and James Webb and things like that, whereas Michael was beavering away in the Netherlands on this project that nobody had ever heard of, a Gaia, which I have to say, I know the amount of effort that Michael and his collaborators put into this, and it's a huge effort. It's not just a scientific effort. And Michael is largely responsible for creating the scientific case for the Gaia spacecraft, which has to be done in great detail and has to be sold to the agency in order to get the funding to do it. That's a major effort. But the whole organization of the scientific community, which was receptive to the results from Gaia, but also the community of people around Europe who had to create the data analysis system. It's a huge data analysis problem when you're dealing with 2 billion stars with multiple observations per star. I mean, this is very comparable, probably more than comparable, with some of the things that are done in particle physics, where they have to look at billions and billions and billions of events. So it's a major computer exercise, but just managing all of these groups around Europe and getting them to coordinate their activities to create this huge computing infrastructure to actually produce the results that we're seeing is enormous. And I have to say, Michael has a special talent for project organization, which is very rare. And I think the reason that Gaia has been such an enormous success within the ESA community is because he was so effective at organizing the case and the talent and so on. And I think it's very apparent from this, although we're all familiar with Hubble and James Webb Space Telescope, the amount of data, very high quality, that's come out of Gaia is absolutely huge. And it's not an instantaneous package. People will be using these data for many, many decades into the future, probably hundreds of years into the future, in order to put together the picture of what's going on. So it's so far from being a trivial achievement to actually create a project of this magnitude and to get it built, all the technical stuff, building a huge CCD array and so on, these huge mirrors mounted with such incredible stability and precision is a very, very major task. So I mean, I talk to Michael about the science a lot, and I know a lot of his essays, and the website has lots and lots of absolutely fascinating information in it, including some of the history of the project. I mean, the engineers who worked on Gaia, some of those have been interviewed on his website, and the stories are fascinating. The story with Rusty Schweickart, the Apollo astronaut, the person who flew the LEM for the first time, his story, connected with asteroid impacts on the Earth, it's a wonderful story. And he's quite old now, Rusty, and he tells this story with great vigor. In fact, I had the good fortune to be an observer for the European Space Agency on the panel in the United Nations, which had to recommend to the Security Council of the UN what kind of action would have to be taken if there were going to be a major asteroid impact. And there were a gathering used to meet in Vienna at the UN a couple of times a year and considered all the possibilities for managing public reaction to such a story, but also organizing the space agencies to perhaps fly missions which would mitigate the impact or avoid the impact. And Rusty Schweickart was on that panel, so I got to know him quite well then. But many other astronauts were on that panel as well. And that was an extraordinary group of people. And I felt very, very privileged to be a part of that. But so I just like to pay credit to Michael for a really magnificent achievement in putting all this together and producing a set of data which is so far ahead of any previous data set in the same field. You saw from the diagram in the beginning the huge increase in the quality and the precision of data. I mean, with Hipparcos and followed on by Gaia, the whole classical astronomy field of measurement of stellar positions I mean, it's been blown out of the water by these missions. It's just a huge contribution and a huge step forward. So thank you very much, Michael.